Good morning all of you. So in continuation with this solution of differential equation, we now get that solution in terms of displacement of particular oscillator motion or a particular oscillator motion body. X is equal to a1 e raised to u1 t, a2 e raised to u2 t. A1 and a2 are the constants. We can determine this a1 and a2 by putting the boundary condition. Putting boundary condition, and we can obtain that displacement x at particular time t. Now, if we consider that four cases, now we discussed that four cases afterwards. Now here one more case is considered. Now here, if you look at this roots of this particular equation, u1 and u2, which are differentiated only by this plus and minus term, Here this root is having plus sign, here this root having minus sign. If suppose this square root term becomes as a 0. If suppose the square root term in both the roots are same, square root term here in this case and here for the second root is same. If suppose this difference or square root term becomes as a 0, in that case these two roots become equal. If the square root term becomes as a 0, these two roots become equal, and that is nothing but a u1 and u2 are equal and is equal to minus c by 2m. u1 and u2 are equal and is equal to minus c by 2m. So these two roots are equal. When only this term in the square root are 0. Term in that square root becomes as 0. Now if we consider this term, these terms becomes as 0. If we put this c by 2m bracket square minus k by m is equal to 0, then we can write c by 2m is equal to under root k by m. Now we introduce one more term. As a critical damping coefficient. This c we already discussed. C is already discussed in types of damping as a damping coefficient. C is discussed already in previous case or damping chapter is a damping coefficient of particular damper C. Damping coefficient of that particular viscous damping C. Now we introduce one more term as a critical damping coefficient CC. So this critical damping coefficient CC is nothing but a damping coefficient C. When these two roots become equal. When such condition observed, when these two roots becomes equal, in that case C is replaced by CC. So when these two roots become equal, the damping coefficient is called as a critical damping coefficient CC. So here we introduce one more term, critical damping coefficient CC. It is nothing but a damping coefficient. In such case, when two roots of that particular equation of motion become equal, that damping coefficient is nothing but a CC, which is we derived as a 2m omega n, Omega n is nothing but a under root k by m, which is called as a natural frequency. Under root k by m is nothing but a natural frequency omega n. So in this derivation, it is related to the free vibration. So in this free vibration topic, instead of writing omega suffix n, it is written as a just omega. So n suffix is absent here. So in free vibration, there is no need to write as a omega n. So it is write as a omega. Here it is write as a omega. It is nothing but omega n in free vibration. In post vibration, we consider that then there are two different terms. Omega n, omega n and omega. In that case, we write as a omega n. So in free vibration, there is no need to write as a omega n. So free vibration omega is nothing but omega n. So this is nothing but CC. This is nothing but a Cc. This is nothing but a Cc or critical damping coefficient. So we get this solution. Again for solution there are two roots. And these two roots again the C by 2m we can rewrite. The C by 2m we can rearrange and we can rewrite as a is equal to zeta omega. Now one more term we introduce as a zeta. One more term we introduce as a zeta. This zeta is a nothing but a ratio of damping coefficient C and critical damping coefficient Cc. Zeta is nothing but a ratio of damping coefficient C and critical damping coefficient Cc. Now we write this, whatever that equation of motion, we write that solution of that particular equation of motion in terms of zeta. We write solution of that particular equation of motion in terms of zeta. So to write in terms of zeta, we just change this C by 2m in terms of zeta. So we rearrange this C by 2m as a divide and multiply by Cc. C by Cc, Cc by 2m. So C by Cc is nothing but zeta and Cc by 2m is nothing but omega. Cc by 2m is nothing but Cc by 2m is nothing but omega. Cc by 2m is nothing but omega. So these are put here, and this C by 2m term now change as a zeta omega. C by 2m term now change as a zeta omega. Now put the C by 2m term zeta omega here in the solution of that particular equation just we derived here, and then it becomes as a a1 e raised to now u1t in terms of zeta we express and a2 plus e raised to u2t. We get this x in terms of zeta. Now this is the solution of that particular vibratory motion having free vibration and having damping case. So for damping and for free vibration oscillatory motion of particular body, we can write that solution x is equal to like this. We can write solution x is equal to like this. So this solution is described displacement x of particular vibratory body, displacement x of that particular vibratory body at particular time t, and having some damping ratio zeta, This C by Cc is nothing but again this zeta is called as a damping ratio. C by zeta is called as a damping ratio. So x is nothing but a displacement of that particular vibratory body at time t and at particular damping ratio zeta. So this is the solution of that particular equation of motion. So x, and from x we can again, if we differentiate this x with respect to time d by dt of x, we can get x dot. If we differentiate this x 2 times with respect to d by dt or d square by dt square of x is nothing but acceleration. So once you have obtained x, then you can find out that velocity and we can find out that acceleration by just differentiating with respect to time. So we get this solution of that particular equation of motion of particular system. So this solution, now if you look at this solution, or we write this solution in terms of zeta, which is nothing but a damping ratio. Now that zeta again have three values. That zeta may be less than 1, zeta equal to 1, and zeta is greater than equal to 1. There are three cases. Zeta may be less than 1, zeta equal to 1, or maybe zeta is greater than 1. So all three cases are called as a, if zeta is greater than 1, it is called as a over-damped case. If zeta is equal to 1, it is called as a critical damped case. And if zeta is less than 1, it is called as a under-damped case. So we discuss these three cases. Like this. So for first over-damped case, when zeta is greater than 1, in this case, Now we consider the roots of that equation. The roots of that equation we just derived as a u1 and u2. We just derived as a u1 and u2. Now in this overdamped case, their roots are real. Their roots are real and unequal. Their roots are real and unequal. Overdamped case. So u1, u2 are real one and unequal. This is nothing but overdamped system case. So now we can write this as a x is equal to a1 plus a2. Now this a1 a2 value we can derive from the boundary condition. That are derived from the boundary condition. And again we put here x is equal to a1 e raised to u1t plus a2 e raised to u2t, that are we already derived. Whatever the derived equation, is valid for the overdamped case. It is valid for the overdamped case. And when you put t is equal to 0 here, this becomes as x is equal to a1 plus a2. This becomes as x is equal to a1 plus a2. And again we differentiate with respect to t. We get x dot value. Again put t boundary condition or time boundary condition, and we can get this a1 and a2. We can get this a1 and a2 value. Then again put this a1 and a2 here, and we get a displacement solution. So in overdamped, this is nothing but a overdamped case solution. Here u1 and u2 are the real one and unequal one. u1 and u2 are the real one and unequal one. So as discussed, there are four cases. Of the roots. Here first case we discussed as a real one and unequal one. Roots are real one and unequal one. And if you plot a displacement versus time curve, for vibratory body or vibratory body displacement versus time plot, then we observe this type of curve. So whatever that amplitude is a reduced to zero. Amplitude nothing but a maximum displacement. As we discussed in the first lecture, whatever that maximum displacement of particular oscillator motion, nothing but amplitude. This amplitude is reduced to zero within a short time. Within a short time t, this amplitude is reduced to zero. This is nothing but a overdamped case. Now second case. Now we slowly move toward the second case. This critically damped case. So this critical damped case, in this critical damped case, zeta is equal to 1. As soon as zeta is equal to 1, it nothing but a roots are equal. Zeta is equal to 1, it nothing but a roots are equal. And the roots are equal as we derived earlier. C by 2m is equal to 100 k by m. C by 2 roots are equal, it means the square root term becomes as 0. Roots are equal, it nothing but a square root term becomes as 0. Then and then only roots are equal, and the square root of term becomes as 0. Then it is called as a critical damped case. When zeta is equal to 1, it is called a critical damped case. Then c by 2m is equal to 100 k by m, and the two roots now becomes as a, for c by 2m we can write as a minus zeta omega. And zeta is again 1. For critical damped case. So u1 and u2 are roots are equal, which are equal to minus zeta omega. Zeta is 1, so it becomes as a minus omega. Now we put this u1 u2 here. Now for when roots are equal, that solution of that particular differential equation is nothing or slightly changes as x is equal to a1 e raised to u1t plus t a2 e raised to u2t. In previous case, when two roots are unequal, that solution we write as a x is equal to a1 e raised to u1t plus a2 e raised to u2t. This t is absent in previous case. When roots are unequal, this t is absent. When these two roots are equal, its solution slightly changes as x is equal to a1 e raised to u1